got to record this. All right. This flow chart again kind of helps you go through the system of determining. Okay, I have a covalent compound. If it's nonpolar, and then obviously the only force, if we go to the left of the flow chart, is London forces. Okay. If it is a polar species, then I have to determine which of the three do I have here. If I'm dealing with an ionic compound in water, then obviously it's the last choice down here, ion dipole. Okay. If it's a polar covalent bond, okay. Now the question is it dipole? Well, if it's hydrogen bonded to nitrogen, oxygen, and fluoride, then it's hydrogen bridging. If it's not, then the only choice you have is dipole. Okay. So hopefully this flow chart kind of summarizes it for you. Now, how do we use these forces? Okay. That allows us to determine the physical properties, actually to compare. Now, we're not going to be able to determine absolute values, but we can determine based on the IMF interaction, whether how strong it is, which one would have a higher physical property of some sort. The physical properties that we're going to talk about is vapor pressure, okay, the boiling point, surface tension, and viscosity. Okay. Now, vapor pressure, you we you've seen this happen a lot. You got a soda pop, a drink, and you open it up and then you close the cap. Well, in that empty area, we have gas molecules in there because you know that if you take that soda pop and you unscrew it, it would make that sound of the gas removing. If I were to able to put a pressure gauge in that empty area, it would have pressure. Okay. Yeah. Okay. So if you think about it, if the liquid attraction to each other are very small and weak, we're going to have more molecules going into the gas phase and the vapor pressure goes up. If the interactions in the molecule and the liquid are very strong, then they're going to hold on to the molecules greater and less molecules go into the gas phase. Okay. And that's determined by the intermolecular forces. Okay. All right. And we know if you have no lid on a container that the air molecules will eventually the molecules will, the liquid will eventually go into the vapor phase. So vapor pressure is in a closed container, how much pressure you have in that empty space in the closed container. Okay. All right. Now, if you have strong IMF forces, you're going to have a lower vapor pressure. Okay. Why? Because the molecules in the liquid are going to be held on closer. They're going to be held on tighter with each other, and therefore less molecules are going to go into the gas phase. Okay. So this diagram shows it. Okay, which has the weaker IMF. Well, A would have the weaker IMF. Why? Because there's more molecules in the gas phase. You can see more molecules up there in the gas phase. And A would also have the higher vapor pressure because we have more gas molecules, okay, compared to B. You see how that works? And so you have a lot of vapor pressure, then that compound, whatever that is, has very weak IMF interactions. Boiling point. Boiling point is that pressure, is that temperature in which a liquid at 1 atmosphere goes from liquid to gas phase. And there's a variety of boiling points. Water has a boiling point of 100 degrees Celsius. Alcohol, ethanol, has a boiling point of about 70 degrees, 78 degrees, I believe. Okay, so there's a variety of different boiling points for liquids out there. and they're all that's determined by the IMF interaction of the liquid. Again, here, if you have strong IMF interactions, you're going to have a higher boiling point because it's going to take more energy to get those molecules to get into the gas phase. So that temperature at which it boils will be higher because those molecules are holding on tightly to each other in a liquid phase, and we have to give it enough energy to break up those interactions. Okay. Also, the same is true for the melting point. That is a melting point that a solid goes into the liquid. And so if the IMF interactions are strong, those solid atoms are holding on to each other. It would take a lot of energy to get them to melt. Okay, so their temperature would be higher. Surface tension, and that's how liquids or molecules interact with each other on the surface. Okay, so for example, strong IMF would have high surface tension. Surface tension, for example, I don't know if you ever noticed when you have your cars dirty and you put water on it, it spreads out, right? Once you clean your car up and you wax it up and you put water in it, it beads up. Well, that beading is what we call surface tension. Okay, so again, if you have um, strong IMF interactions, you're going to have high surface tension. Okay, and this here is an example of what I was talking about. The question is, which liquid has a higher IMF, A or B? In this case, A, because the molecules are being held onto each other tighter. So it's forming that hump. If the molecules are not holding onto each other very strongly, that liquid just spreads out over the surface. Okay. All right. Viscosity. That is a measure of how thick a liquid is. Good example I used before has been water and honey. Okay, honey is very thick. It has a higher viscosity and therefore will flow slowly compared to water. Again, the that flowing or that viscosity is governed by the IMF interaction. So in this example, we're asking you, does oil flows slowly? It has a high viscosity. Okay. We know that water or an alcohol, for example, has a low viscosity because it flows much more rapidly. Okay. And so stronger IMF will give you higher viscosity simply because the molecules are being held on to each other uh, much greater than the IMF interactions that are weaker. So let's compare two things. Let's compare ammonia and fluorine, and we're going to determine those four physical properties. Who's going to have a higher, who's going to have a lower boiling point, etc. But before we can do that, when we compare any two molecules, and like I said, we can't give absolute values, but we can compare two different molecules and determine who's going to have the higher boiling point, who's going to have the higher viscosity, vapor pressure, and surface tension. And we do that by first determining whether it's polar, and then from there determine uh, whether it's either polar or nonpolar. Okay, and then from there determine what force it has. Okay, and so ammonia has that particular formula, NH3. We wrote the Lewis dot structure for this before, and we have a lone pair in the atom, in the central atom of nitrogen. Therefore, it is very polar. Fluorine, diatomic, very nonpolar. And so for ammonia being polar, plus you got hydrogen bonded to nitrogen, its force is hydrogen bridging. Fluorine is diatomic, therefore it is nonpolar, and the only force it has is London forces. London forces, once we determine what forces is associated with the compound, now we determine which one is the stronger one, and we know that hydrogen bridging is much stronger force than London forces. Okay, and knowing that, then we're able to answer some questions comparing ammonia and fluorine. The first question, which we already answered, is which has the stronger IMF? Well, of course, ammonia does because it has hydrogen bridging forces. Okay. Next question is who would have the lower boiling point? Well, think about it for a moment. If it has a lower boiling point, that means the molecules are interacting in the liquid phase very weakly. So London forces are not as strong as hydrogen bridging. Therefore, fluorine would have the lower boiling point. Okay. Which one is polar? Well, we answered that earlier. Okay. Hydrogen bridging obviously is ammonia, I should say, is polar. Okay. We needed to know that so we can assign what force. And which has a higher vapor pressure. Again, to have a higher vapor pressure means that the molecules in the liquid are held on to each other much weaker. And again, here, fluorine has the weaker force. Okay, and which is the least viscous if they were both liquids? Okay, again, fluorine would flow much more readily than ammonia, simply because it has the weaker force. And then again, the last thing, which has the more surface tension? Again, ammonia would, simply because it has the stronger force. Okay, so we can summarize this and say that as the IMF increases, viscosity increases. Okay, and the boiling point increases, the surface tension increases, but the vapor pressure decreases. Okay, so it makes pretty good sense when you think about it as far as viscosity, boiling point, and surface tension, because if the IMF is strong, it's going to hold the atoms relative to each other much strongly than something that has a weaker IMF interaction. Therefore, there's going to be less molecules in the gas phase, and therefore the vapor pressure would be less. Okay. Not much to say about water here. We're just gonna talk about it very quickly. Just we did this before in Lewis dot structures. We determined there's two bonding electron pairs, and then there's two non-bonding or lone electron pairs at a bent structure. Much less, the bond angle is much less than 109.5. Okay, and water is very, very polar. Okay, and it has very strong hydrogen bridging forces between the molecules. Okay, properties of water, like I said, very polar, high IMF, very low vapor pressure, boiling point 100 degrees, melting point 0 degrees, very high surface tension, and one unique property about water when it freezes is density gets less and therefore floats. Not very other compounds, molecules can do that. There's something unusual about water, very unique. And there's some structures that in the solid, water tends to align themselves. Okay, let's briefly talk about heating something because it's related to the IMF interactions. Okay, and so we can use this example here. This could be readily be water. We know that we can take water, freeze it, and we're in the solid. Let me get something here. Let me get an arrow. So in this region, in low temperature, water is in the solid. And then as we heat it, obviously, we get into the liquid phase. And then we continue to heat it, we'll get into the gas phase. Okay. So we got temperature going up. Okay. And then the progress of it as we go along the x-axis from left to right, that's as we heat. Something interesting here, if you look at this graph, is that we have two plateaus. We got a plateau here and a plateau right here. Okay. Now, when we heat a liquid, it remains in the solid phase and the temperature goes up. But throughout that rise in temperature, as I proceed, it remains solid until we hit that first plateau. When we hit that first plateau, the solid now becomes a mixture of solid and liquid. And so that's that first plateau. So we got a mixture right here of solid and liquid on the plateau. Note that the temperature remains constant. So you can keep adding heat to this plateau and it will never get any greater in temperature until such time that all of that solid has been converted to liquid and we get another rise. Okay, we get another rise going up. In this area, all the molecule is in liquid phase. Okay, and guess what? We hit a second plateau. The temperature again is constant. Right here, here's that first plateau. There's this, the first plateau is right here, and then the second plateau. But in this second plateau, we have a mixture of liquid and gas until such time that all that liquid has been converted to gas. Then we get another rise in temperature right here. Okay. And so we have two plateaus. So as you're boiling water, for example, to cook something in the kitchen, and it is boiling, you can see water is boiling. By adding more heat, you're not going to get the temperature any higher. Your temperature is going to remain at 0 degrees, so save your energy until such time that you have evaporated all the liquid. Then you get a higher temperature. Okay. So this is what we call a heating curve of what generally happens to molecules when we heat them, when they're in the solid and they transverse to the liquid and go on to the gas. Okay. And this again is basically what I just wrote here earlier with my arrows, but you can see at the plateau, you have a mixture of solid and liquid. That's where the solid is going all to liquid. And then you get a rise in temperature until you hit the second plateau. And at that point, the liquid is being converted to gas. And then eventually you get a second rise. Okay. So at these plateaus, again, no matter how much energy you put into it, you're not going to increase the temperature anymore until such time this plateau there and this plateau here. Okay. Until such time, the temperature will go up until such time you move everything to the next phase. Okay, so be familiar with this type of graph. Okay, because you can see how questions could be asked. At what point do you have a mixture of solid and liquid, things like that. At what point is it all liquid? At what point is it all gas? Those type of questions can easily come up. Okay. And this slide here just basically summarizes what I just talked about. Temperature remains constant during these phase changes. All the energy that you put in during the plateaus is being absorbed by the compound, the molecule, to break up that interaction. Okay, just like I said earlier about honey, how viscous it is because those forces are very strong. How do we make it less viscous? We heat it. By heating honey, it makes it more liquidy. The viscosity gets lower. And what you're doing is you're breaking up those forces that we've been talking about between molecules. You're breaking them up so they're not interacting with each other as much. You can see how if you get butter, you take it out of the refrigerator, it's solid, right? Put it on the pan, heat it up, you cause it to go into liquid. So, and all you're doing is breaking up those forces. Okay. Which brings me to the end of chapter 14. Okay. Any questions, Luya? Did I pronounce that right, Luya? Yeah, okay, thank you. All right, well, what I want to do is I want to jump into chapter 15 because I got a few minutes here. You know what? 15 is very short. Why don't we stop it here? And it'll be our last chapter, and we'll finish that on Monday. Remember, Thursday, tomorrow, is that tomorrow? Is the official holiday, so we won't have a lecture here today. But I will be here for office hours if you have any questions. Okay? So if you have any questions, feel free to ask now. If not, let me stop